Operational amplifiers, op-amps, are fundamental building blocks in modern electronics due to their versatility and efficiency. Originating from analog computation, op-amps are now integral to applications ranging from audio processing to precision measurement systems. This chapter explores the key characteristics, configurations, and practical applications of op-amps, offering insights into their ideal behavior and real-world limitations. With their ability to amplify, integrate, and differentiate signals, op-amps empower engineers to design circuits with exceptional functionality and accuracy. 1. Ideal operational amplifier, op-amp. Characteristics: an ideal op-amp has specific theoretical properties that make it an excellent building block for a variety of electronic circuits. 1. Infinite input impedance, meaning no current flows into the op-amp's input terminals. Sound why this matters. This prevents the circuit connected to the op-amp from being disturbed. For example, when measuring voltage in a sensor circuit, we don't want the op-amp itself to draw current and interfere with the measurement. 2. Zero output impedance, meaning the op-amp can deliver the exact required voltage at its output, regardless of the load. A real-life example. In audio systems, the speaker can demand varying amounts of current without affecting the audio signal. 3. Infinite open-loop gain, A, meaning the op-amp amplifies the voltage difference between its two inputs to an enormous degree. Practical insight. In reality, this gain is finite but still very high, enabling precise control when feedback is applied. 4. Infinite bandwidth, meaning the op-amp can amplify signals of any frequency equally. Sure, practical limitation. Real op-amps have a frequency range, but modern op-amps can handle audio to radio frequencies effectively. 5. Zero common mode gain, meaning the op-amp ignores signals that are common to both inputs and only amplifies the difference. Example: when measuring small voltage differences in noisy environments, such as a heart rate monitor, this property helps reject noise signals. 2. Basic configurations: op-amps are versatile and can be configured in different ways to achieve specific purposes. Here are two of the most common configurations. Inverting amplifier. 1. How it works. The input signal is applied to the inverting terminal, sighing, and the output signal is inverted, flipped in phase, while being amplified by the ratio of two resistors. 2. Example: if you input a 1V sine wave and the gain is +10, the output will be a +10V sine wave inverted. 3. Where it's used. Filters in audio systems to manipulate sound frequencies. Non-inverting amplifier. 1. How it works. The input is applied to the non-inverting terminal, plus, and the output retains the same phase as the input while being amplified by 2. Example: if a microphone outputs a weak 0.2V signal, a non-inverting amplifier with a gain of 50 can amplify it to 10V for further processing. 3. Where it's used. Used to amplify small sensor signals without flipping their polarity. Voltage follower. 1. Special case. A non-inverting amplifier with a gain of 1. So the output equals the input. 2. Purpose. To buffer a high impedance source and provide a low impedance output. 3. Example: connecting a high impedance thermistor to a low impedance ADC, analog to digital converter. 3. Advanced configurations. Summing amplifier. 1. What it does. Combines multiple input signals into a weighted sum. 2 equation. 3. Real-life example. Audio mixing consoles where signals from different instruments are blended together. Difference amplifier. 1. What it does. Amplifies the difference between two input signals while rejecting signals common to both. 2. Why it's useful. It helps in noisy environments where both inputs pick up the same interference. 3. Example: measuring voltage across a shunt resistor in motor control circuits. Instrumentation amplifier. 1. Key feature. Combines the benefits of high input impedance and difference amplification. 2. Real-life use. Medical devices like ECG monitors, where precise measurement of small differential signals is critical. 4. Feedback. Concepts. Feedback is a fundamental concept that controls the behavior of op-amp circuits. 1. Negative feedback. How it works. A portion of the output signal is fed back to the input in such a way that it stabilizes the output. Benefits. Increases accuracy, reduces distortion, and makes the system less sensitive to component variations. Example. Stabilizing the gain of a power amplifier to prevent overheating or signal clipping. 2. Positive feedback. How it works. Feedback reinforces the input signal, often leading to oscillation or bistable operation. Where it's used. Oscillator circuits and comparators. 5. Non-ideal characteristics. Real op-amps deviate from ideal behavior in the following ways. 1. Finite gain and bandwidth. High-frequency signals are not amplified as much. Example. Audio amplifiers may distort sound at very high pitches. 2. Offset voltage. A small, unintended voltage difference between inputs leads to output errors. Example. In a sensor circuit, this could result in a constant bias error in measurements. 3. Input bias. Current. A small current flows into the input terminals which can affect precision circuits. 6. Integrators and differentiators integrator. 1. How it works. The output represents the integral area under the curve of the input signal. 2. Key feature. A capacitor is used in the feedback loop instead of a resistor. 3. Real-life example. Charge measurement circuits in energy meters. Differentiator. 1. How it works. The output represents the rate of change, slope of the input signal. 2. Key feature. A capacitor is used in the input path. 3. Real-life example. Edge detection in image processing or spike detection in biomedical signals.